In section 1.2, we talked about measuring line segments, and in section 1.3, we're going to talk about measuring angles. So one of the things that makes angles different than line segments is the units of measurement. With segments, it could have been inches or centimeters or millimeters, feet, miles. But with an angle, it's always degrees. So our measurement will always be done in degrees. And you would use a protractor to measure an angle. There's also some new symbols that we need to be aware of. If we see the little M in front of the angle symbol, which is something new, we didn't see that in section 1.1 or 1.2, that means we're looking for a number. What is the actual measurement? So the little M stands for the measure of. So anytime you see that little M, we're looking for you to figure out something related to a number, applying an actual number to the angle. All right, so the first thing we're going to do in this set of notes is just simply learn how to classify angles. And so there's 4 different classifications for angles. An angle can be an acute, a right, an obtuse, or a straight angle depending on its measurement. So if it's an acute angle, it would be less than 90 degrees. A 90-degree angle is what I always call the perfect corner. So if an angle is 90 degrees, the 2 rays are going to meet at a perfect, what I call, corner. So that would be a perfect corner right there. But in this picture, that's not what's happening. Our rays are meeting at something less than that. So if a angle is a perfect corner, it would be something more like that second picture. So let's start there. If you have that perfect corner happening, that's a right angle, and that means the measurement is 90 degrees. But if we go back to that first picture, you can see that angle is bending less than 90 degrees. So that means the measurement would be between 0 degrees and 90 degrees. So maybe 1 degree, maybe 89 degrees, anywhere in between 0 and 90. If we move over to the third picture, I kind of don't like where that A is. That A should really be closer to the vertex. That measure of angle A there, you can see is bending bigger than 90, because again, if it was 90, it would be straight up and down and meet at like that perfect corner. So since that's not happening, it's going bigger than that, we would call that an obtuse angle. So any angle that is greater than 90 degrees, but less than 180 degrees, that would be considered an obtuse angle. And an angle could be, it looks like a straight line, but it could be an angle. Remember, we're talking about things that sometimes move in a circular motion. So if you think about the hands of a clock, if the hand of the clock moved from 3 o'clock over here, over to 9 o'clock over here, that would be 180 degrees of motion. So it looks like a straight line, but really if we're talking about circular motion, it would be a straight angle instead. It just depends on what the situation is. So a straight angle that looks like a straight line is actually 180 degrees. So if we come down to example 1, we're being asked to classify each angle as acute, obtuse, right, or straight. So in that first picture, example 1A, hopefully you notice that that angle is bigger than 90 degrees. If you put a corner of anything, like a perfect corner, so if you had a piece of paper and you stuck it in this next to that vertex, that's where it would be. This bends bigger than that, right? It expands bigger than 90 degrees. So this first picture, that is an obtuse angle. Whereas in the next picture, again, that perfect 90 would be this way. That is bending in from the 90. That is less than the 90. And so this would be considered an acute angle. And even though C looks like a straight line, the directions say think of it more as an angle. I know sometimes it makes it easier if they actually would have put that vertex in the middle. But even without that vertex, the directions are asking you to classify it as an angle. So if you see what looks like a straight line, we can also think of that as a straight angle. So we're going to classify that one as straight. Those first 3 pictures were pictures, whereas the next 3 examples are numbers. So even though we don't see the picture of the angle, it's saying, well, if the angle measurement was 90, what would you classify it as? You would classify it as a right angle. Where in example E, if you were asked to classify something that was 52 degrees, you know that's less than 90, so you would call that an acute angle. And in example F, since that is bigger than 90 degrees, we would call that an obtuse angle. So one of the things we want you to be able to do with angles is to classify them as acute, right, obtuse, or straight, depending on their measurements. Another thing we want you to be able to do with angles is apply what's called the angle addition postulate. The angle addition postulate works very much like the segment addition postulate. If an angle moves from, well, let's think of that clock again. So let's say maybe this is 1 o'clock, this is 3 o'clock, and this is 4 o'clock. So if an angle, the motion of your hand on your clock moves from the R to the T, right? Think about that moving like that. That's one of the angles you could measure. If the then hand continues to move from like that T to the V position, that's another angle you could measure. And then if you want to know the total amount of movement, that would be this big movement from R all the way to V. So the way I like to think of this postulate is you have these two smaller inside angles, I call them. So we're going to call this inside angle 1. Then we have inside angle 2. And I'm going to erase these clock numbers because it's just one way to think about angles is by thinking of a clock, but we don't have to think of it as a clock. So we have those two smaller movements if you do think about the hands of the clock. So those two inside angles add up to that whole big outside angle. I sometimes like to color code this. So if we think about the first angle as this yellow angle, the second angle as this green angle, and the big outside angle is the blue angle, then you can think of inside yellow, inside green angle adds up to outside or whole blue angle. That's another way to think of it, kind of as a color coding thing. So inside 1 plus inside 2 equals the whole thing, the whole big outside angle. And when I write things like inside and outside and I don't use those letters that you see directly above it, it's because I'm trying to simplify the concept. It really is a pretty easy concept that two smaller things can add up to the whole big thing. And that's what's happening with angles, very much like it happened with segments. So if we come over here to example 2, we have a picture of 3 angles actually. Remember, we have two inside angles and an outside angle. And so if you like to color code, you can take your highlighter and you can say, okay, there is this inside angle that I'm calling the yellow angle. And then there is another inside angle that I'm calling the green angle. And the big outside angle is the whole thing all the way from C to E. And so the inside angle, if I was going to give it a 3-letter name, it would be, the yellow one would be CDH. So the yellow one would be this one right here, CDH. The green one would be, well, I can't see my colors here, EDH or HDE. So the other one, the green one, would be HDE. And the big outside blue one would be CDE. So sometimes color coding helps you figure out what's going on. So it says CDH is the yellow one is 76 degrees. HDE is the green one, which is 70 degrees. Those are those two smaller angles. And then what they want to know is how big is this big outside angle. You can call it X, you can give it a question mark, whatever you want, but the two insides add up to the big outside. I sometimes have people want to do the outside one back here and put the question mark back here. That's fine. Whatever makes the most sense to you. I tend to do it where I have it labeled, so I'm going to leave it there. So that big outside angle, which is CDE, so the measure of angle CDE is going to be the two smaller ones, 70 plus 76 added up. Again, that's just called the angle addition postulate, and you'd get 146 degrees. Let's try it again. Again, color coding is really helpful when we're dealing with angles. It asks us to find HIA. So if we trace HIA from H to I to A, just put your pencil on H, go to I, and then finish at A. That one is what we're being asked to find. So I'm going to put a little question mark on that one. I don't know that one. What else have they given us? They've also told us that HIJ, again, put your pencil on the H, go to the I, and then finish at the J. Whoops, that's not really working for me there. That big outside angle they're telling us is 114. Again, I have a habit of labeling it out here, but if you wanted to label it out here as 114, if you prefer it there, that's fine. But I'm going to leave it where I usually do it. And then AIJ, if we label that one, A to I to J, put your pencil on A, go to I, and then go to J. That one is 44 degrees. So that blue angle is 44 degrees. And so this time we know that the little one is missing. So the inside plus the inside equals the outside of 114. So if you like algebra, you can do x, call the question mark x plus 44 equals 114. Subtract 44 from both sides. And you get a missing x of 70 degrees. That's if you like doing it with algebra. If you rather just think of it as subtraction, right? If I know the big hole outside is 114, then my missing angle, which again, my missing angle is angle HIA, is just going to be the 114 minus the 44. So some people just do it with subtraction. Other people like to use algebra. Either way, you should know that that missing inside angle is 70, because 70 and 44 add up to the outside, which is 114. All right, those are again what I call numeric because the angles strictly have numbers on them. There's no algebra involved. But if we go down to example 3, there's some algebra involved. So I can't stress enough that when we're dealing with angles, it really does help to highlight them. I mean, line segments are a lot easier, so I didn't really suggest that you highlight anything in 1.2. But in 1.3, I don't know why, but angles tend to confuse students more. So the way it works, again, if they're telling you find x, if the measure of angle LMN is 128, I say take a highlighter out, put it on L, trace to the M, then trace to the N. That's that whole big outside part. See how the V is in between everything? The outside big angle is the one that is LMN. And they're telling you that one is 128 degrees. So the whole thing is 128 degrees. One of the smaller inside angles is LMV. So again, put your pen or your highlighter or whatever you're going to use on the L, trace to the M, finish at the V. So you're tracing this small inside angle. They're telling you that one is x plus 35. Going to squeeze that on the inside. And then finally, they're telling you that VMN, the measure of angle VMN, is x plus 113. So if you put your pen on V, go into the M, finish at the N, that inside blue angle they're telling you is x plus 113. So those outside letters, LMN, that represents 128. Again, that's the whole angle, all the way from L to the N if the hands of the clock were moving. So the two inside pieces, the x plus the 35 plus the x plus the 113 is going to equal 128. When we were doing segments, we talked about combining like terms. So we have like terms being on the same side of the equal sign. So I have a pair of x's, right? 1x and 1x makes 2x. I have some constants on the same side of the equal sign. So if I add them up, I get 148 equals 128. Subtract your 148 off of both sides, and you get 2x equals negative 20. Divide by 2, and your x is negative 10. Now, because the directions told you to find x, this is actually the final answer, right? It just says find x there. Don't forget that negatives might or might not make sense. In this case, they do make sense because if you were to plug the negative 10 back in to those two inside expressions, you would not get negative angles. You would have positive angles. All right, so that's the angle addition postulate, very, very similar to the segment addition postulate, where the two smaller angles add up to the big angle. The two smaller inside angles add up to the bigger outside angle. For whatever reason, students sometimes struggle to know where to label the angle, so maybe use a color tracing method to do that. All right, the last part of these notes has to do with, did a big angle get cut in half? And how am I going to know if it got cut in half? Well, just like we did with segments, we might see some keywords, or we might see some markings, or we might see some symbols. So the words that we might see would be the word congruent. If they're telling you in this picture there are two congruent angles, that means they have the same measure. So, for example, if one of them's 60, then the other one's 60. That's one of the words we might see. Another word we might see is bisector, very similar to when we were working with segments. So if you hear that something's been bisected, it means it's been cut in half. So a bisector in this picture would be that KM. They're saying ray KM is cutting that big outside angle that I'm going to trace in blue in half. So up in the pictures that we did in example 2 and 3, nothing was being cut in half. We didn't see anything like the word bisector or the word congruent. In these next pictures, we're going to see things like the word congruent or the word bisector. But there's some other things we might see. We might see something that's called arc marks. So the arc marks are these, they should look a little curvier. They're not super curvy here, but these little markings right here, they should look a little bit more curvy. Those are called arc marks. And since the angles are marked with the same kind of arc mark, meaning there's different kinds. There could be a single arc mark or a double arc mark. So let me show you that. If I had a picture where one had a single and one had a double, that wouldn't be marked the same. We wouldn't be able to assume the two angles were equal. But if they both have single markings, like I just drew there, or even if they both have double markings, or they both have triple arc marks, as long as they have the same number of arc marks, that's trying to communicate to you that those angles are identical, the smaller angles in the middle. So in this original picture, those two smaller angles, those two, again, what I'm going to call inside angles, those have the same measurement because there are what are called arc marks, identifying them as identical. So I have inside angle 1 and inside angle 2. And again, we could talk about the whole angle, but often we're not going to have any information about the whole angle because we don't need it. If we know the two inside angles are equal, we can just set them equal. We do not need this whole big outside angle because it's not necessary. So you really won't see that, even though inside plus inside is still equal to outside. We won't be able to add them up to the outside because that piece of information will be missing because it's not necessary. All right, so if you read, the final thing that you could read is what's happening below. If you read that you have equal angles, so you can see that they're saying the measure of angle LKM is equal to the measure of angle MKJ. Well, of course, then you know the two halves are equal because it says so. That's what the equal sign means. And the final symbol you could see would be the congruent symbol. If they use the congruent symbol instead, then they get rid of the M's. The M's mean we're going to talk numbers soon. When they don't put the M's and they use the congruent symbol, that means we're not going to use numbers. We're just going to say, hey, they happen to be equal. We're never going to apply numbers to them. All right, so to summarize this idea, oops, let me switch to a different pen here. We just say inside 1 is equal to inside 2. And we have to have some proof of that. Again, the word congruent, the word bisect, the congruent symbol, the equal symbol, or some arc marks. If we see any of that, we know those two smaller inside angles are equal. So in example 4, we do see that word bisect. So always look for those key words to see if there's any reason you should know that the two halves are equal. So it says ray BD, which is this ray that I'm highlighting in yellow, is bisecting angle ABC, which is this big blue angle. Put your pen on A, go to B, and at C. That blue angle is being cut in half by that yellow ray. And then they go on further to say that angle ABD, which will be, let me pick another color here, so let's pick green, from A to B to D is this green angle. That angle's 34 degrees. So if we make that angle 34 degrees on the inside, we immediately know, because of this word bisect, that the other side is 34 degrees. So let's see what they're actually asking for. They're asking for the measure of DBC. DBC, trace it, is one of those smaller inside angles. It's the one I just put the 34 on. So the measure of angle DBC is also 34 degrees. They're also asking for the blue angle, ABC. That's what I had highlighted in blue. So the measure of angle ABC is 34 plus 34, because I said the inside plus inside still equals the outside, but do we care? Well, in this problem we do, because they're asking about it. They're asking what that outside angle is, so we're going to add up the two 34s and make 68 degrees. All right, and finally in example 5, we're just going to do that same idea, but this time we're going to use some algebra. So how do we know we have two equal angles? We do not just look at it and think, hey, they look equal, so they must be equal. We have to have evidence. We have to have proof. So the proof we have is right here. I'm highlighting it in green. We have a congruent symbol. It's saying angle ABD, which I'll highlight in green, is equal to, or I'm sorry, congruent to angle CBD, which I'm going to highlight in yellow. So the green angle and the yellow angle are equal in size because of that congruent symbol. So when they tell me ABD is 6x plus 3, ABD is this green one, 6x plus 3, and they tell me that CBD is 8x minus 7, and they give me no information about this big outside angle. And remember, you never put an X out here. That would be wrong. You have X's in the picture. How would you know that the X on the outside would be the same? You don't know that. And you don't need that, because I don't need to add the inside plus the inside to the outside in this picture. I know the two angles are equal. So all I need to do is take 6x plus 3 and set it equal to 8x minus 7. I don't need the outside piece if the angle was cut in half. And then I just use my algebra skills. So if I subtract 8x from both sides, because again, my variables are on different sides, I get negative 2x plus 3 equals negative 7. If I subtract 3 from both sides, I get negative 2x equals negative 10. Divide by that negative 2, and x equals 5. That is one of my answers. It did ask me to find x, so that is one of my answers. But furthermore, they want to know what is the measure of angle ABD. So they ask me a second question here. So again, if you trace ABD, you see that that's the one that's been highlighted in green, which is the 6x plus 3. So 6 times the x of 5 plus 3 equals 33 degrees. And that has answered the question, but if they had wanted the other angle, I would know it's also 33 degrees, right? These both must be 33 degrees. Plug in 5 for that 8x minus 7, and you would get 33 degrees. If they asked me about the whole big thing, it'd be 66 degrees. Now, they didn't ask that, right? They didn't ask that, but that would be true of any angle that's been bisected. The other half would be identical, and you could add them together to get the big angle. But the final answer, the only thing they actually asked for, was x equals 5 and the measure of ABD is 33 degrees. All right, so to summarize, we're asking you to be able to classify angles as acute, right, obtuse, or straight based on their measurements. We're asking you to be able to apply the angle addition postulate, which means add up the two smaller inside angles and set it equal to the outside angle. Use your algebra or your math skills to solve. And sometimes instead of doing that, you would just simply set the two smaller angles equal to each other because you see the word either congruent, bisect, maybe you see arc marks, maybe you see an equal sign. Somehow you have a vocabulary word, a marking, or a symbol that lets you know the two halves are equal. And in that case, all you have to do is set inside 1 equal to inside 2, and you don't need to worry about the whole big outside angle.